All right, so then let's get started. So welcome everyone to another instance of the String Fino seminar. So today we have two speakers. The first one is David Wu from Harvard, talking about the species scale in diverse dimensions. So please, David, the floor is yours.
Oh, thank you. It's a great honor and pleasure to speak at this seminar series, and I thank the organizers for giving me this opportunity to present some of my work. And so today I will be talking about species scale in diverse dimensions, which is a work that I've done with Damien, Kumran, and Max, and which resulted in this paper on the archive last year. Right, so as the title suggests, this project concerns the species scale. So to really understand why it's called the species scale, it traces its origin back to what's known as the species problem, posed in the late 90s. So the general setup for this problem is that we start by considering a large amount of light species, say in a theory of quantum gravity, with a naive energy cutoff of a Planck scale. So then if we look at the black hole, what Bekenstein-Hawking entropy would naively tell us is that if we trust our energy cutoff to be of order m Planck, and we normalize it to be of order 1, then the entropy of the minimal black hole at which we would trust the Bekenstein-Hawking entropy would be of order 1. But in the presence of these large degrees of light species in our theory, we can toss them into the black hole, which would suggest that at the same time, the entropy would be of at least the order of this curly n. So this apparent contradiction between what exactly is the entropy of this minimal black hole is what's known as the species problem. So then in the late 2000s, Diwali and collaborators, and also a lot of other brilliant physicists who arrived at a solution which tells us that in the presence of these large number of light species, the energy cutoff of your quantum gravity theory is no longer of order m Planck. Instead, what we should do is we should consider a lower energy cutoff, which is less than m Planck, which accounts for these light species that are present in our theory of quantum gravity, such that the radius of the smallest black hole can be described in terms of these light species. So as this lower scale is solving the species problem, hence it's called the species scale. But as this solves the species problem, because of the difficulty of interpreting what this exact notion of light species is in a theory of quantum gravity, it still remains difficult to compute. But nevertheless, the intuition from that picture is that in an EFT description of quantum gravity, the description breaks down when the curvature reaches the size of the minimal black hole in your theory. So with that intuition, what we can do is we can write down the effective action for the theory by starting with the Einstein-Hilbert term coupled to a massless scalar field or light scalar field. So then what we can do is we can add higher derivative corrections to this term in the form of the following. And in this notation, this curly O operator is a dimension 2n operator that contains contractions of Riemann tensors. And just to ensure that we are dimensionally consistent with our Einstein-Hilbert term, we have to normalize it with some mass scale. And in this case, in this expansion in particular, we normalize it by the Planck scale, where we can compute these coefficients appearing in front of these higher derivative corrections as functions of these light or almost massless or light scalar fields. But incorporating the idea that species scale, that the EFT itself should encode information about what the size of the minimal black hole is, instead of still only including Planck scales in our higher derivative correction, what we should do is instead normalize these higher derivative corrections by this new mass scale, which is the species scale. And in this case, by examining this rewritten form of the higher derivative corrections to the Einstein-Hilbert term, we can see that the EFT description of quantum gravity now breaks down when the curvature is of order species squared. So what this tells us is that even though we have arrived at a different definition of what the species scale is, namely by reading off coefficients of higher derivative corrections, it still nevertheless arrives at the same conclusion that the species scale reveals information about what the size is, what the size of the smallest black hole we would trust from an EFT description of quantum gravity. So with that, we arrive at the definition of the species scale that we will use in our project, which is the species scale is the UV energy cutoff at which corrections to the Einstein action become important. And in particular, if we can write down these coefficients of higher derivative terms, then we can just readily read off what the species scale is. However, as suggested by the series, as suggested by the higher derivative corrections, there are an infinite number of possible terms that we should consider. Nevertheless, there are only quite a few that are exactly computable and protected by supersymmetry and have been written down explicitly. And so a general idea is to just simply examine the possible coefficients that one can compute and look at the maximal value of those coefficients and define that as the upper bound of the species scale. And the highlight of this definition is that in this vein, we would be able to define a species scale that is moduli dependent and different from Diwali and collaborators' solution is that we can actually write down what the species scale is and compute it everywhere in the moduli space. So now that we are able to write down the species scale, a question that we should that motivated us to continue with the study is what exactly can we learn from these moduli dependent quantity, and more specifically, what can we learn about the moduli space structure and geometry by studying this moduli dependent quantity. So in the past, we have seen tremendous progress in understanding corners of the moduli space, specifically pertaining to the asymptotic limits. In particular, in the context of emergent string conjecture, which is put forth by Lee, Lersch, and Huygens in 2019, they have been able to classify that in these asymptotic region of moduli space, we can only expect two scenarios to occur. One is a decompactification at which the effective field theory description, at which we would have a higher dimensional effective field theory description emerge in this limit. And in the other limit, we would it would correspond to an emergent string limit where the lambda species scale is then set by the string scale. But nevertheless, with this tremendous progress, we still have this gap that exists in between these asymptotic regions in moduli space. So the hope is that as we have a really good or as we are improving our understanding and now have a really good understanding of what happens in these asymptotic regions in moduli space of quantum gravity, with this moduli dependent physical quantity, which is lambda species in our case, what we can start asking the question of what happens in the interior of the moduli space. So in a paper by Damien, Cameron, and Max in 2023, they were studying the species scale in the context of 4D equals to 2. And what they observed is that similar to what the distance conjecture suggests, but in the context of an energy cutoff, the species scale decays as an exponential as we approach these asymptotic regions in moduli space. And in particular, it behaves as if in a similar spirit as the distance conjecture, which scales as an order 1 coefficient times the distance we traverse towards the asymptotic region. And similar to what people have accomplished in the sharpened distance conjecture, the order 1 coefficient at which it dictates how fast our energy cutoff is descending as we approach these, or decreasing as we approach these asymptotic region, these order 1 numbers can be determined given the knowledge of knowing what limit we're approaching in the asymptotic region. But the additional information now is that we can connect these asymptotic regions by the species scale. So we have a complete, we have a function that is defined everywhere in the moduli space. So by extrapolating our information from knowing how fast these energy cutoffs descend in the asymptotic region, what Damien, Cameron, and Max observed is that if we look at the slope of the species scale, not only is it bounded by this 1 over d minus 2 in the asymptotic region, this inequality holds globally in the moduli space. Not only and this was initially studied in the context of 4D n equals to 2, with CC scale being defined in relation to the genus 1 topological string amplitude. So with that, now with our understanding of how to read off species scale from higher curvature corrections, the coefficients appearing in front of higher curvature corrections, in this present project, there are several things that we want to achieve. So the first thing is to see that we can actually compute the species scale, not just in one dimension or one setting of a certain amount of supersymmetry, but rather in a diverse dimensions and with diverse amount of supersymmetry. And in each of the settings, we want to compute this lambda species and to see that it actually is defined everywhere in the moduli space. And with that definition and computability that we have, we wish to compute what's called the desert point, which was which is a term coined by Cody, Miguel, Camarena, and Irene, which is but in this context, the desert point that we identify with is the point in the moduli space at which the species scale is maximized. And another thing that we want to compute is the diameter of the moduli space as a function of a lower effective energy cutoff, which is less than the maximal value of the species scale. And what we mean by the diameter is that for any constant slice in species scale in the moduli space, the diameter is identified as the maximal distance between any 2 points in that slice along in that subspace in the moduli space. And at last, what we want to see is that similar to the observations made by Damien, Camarena, Max, is that as we approach these different asymptotic regions, we want to verify that in each of these cases, in different dimensions and different amount of supersymmetry, we will always be able to observe an exponential fall off. And furthermore, with that observation, we want to further provide evidence that if we study this gradient of the species scale across the entire moduli space, we want to show that it also obeys that relation, which is this is bounded by an order 1 number that only depends on the dimension that we are in. So with that, if there aren't any questions, I'll dive into specific examples that we have looked at. Okay, sweet. So the first example is in 10 dimensions and with maximal amount of supersymmetry. And in this case, the first curvature correction comes in at r to the 4th, and this coefficient has been studied in the late 90s by Michael Green and collaborators. And the exact form is as follows, where the first term comes from a tree level contribution and the second term comes from a 1 loop contribution. So and in this particular form, lambda is the canonically normalized dilettante of the theory. So with this expression of the species scale by reading off the curvature, the coefficient appearing in front of the r to the 4th correction, we can plot its behavior as a function of this canonically normalized scalar. And we observe that where the vertical axis is normalized by m-Planck, we see that everywhere in the moduli space, our notion of lambda species is indeed less than the Planck scale, which is a good sanity check that although we're not explicitly solving the species problem, it does tell us that the species scale is lower, that the energy cutoff of our theory that we define is less than Planck scale. So that's a good check. So continuing from that, as we are able to compute the species scale across the entire moduli space, we can identify the point at which it is maximized and compute its value, which is located slightly off-centered, and that is indicative that the 2 asymptotic regions that we will approach in type 2A string theory are different limits, so that we won't get a completely symmetric behavior of the species scale as a function of the dilettante. Furthermore, with a effective energy cutoff mu, we can compute the diameter of this field space that is by simply setting the species scale to by simply inverting the species scale and solving for the diameter. And this is the exact closed form expression for that. And at last, what we see is that away from the center of moduli space, the behavior of the species scale does indeed closely mimic and behave as an exponential falloff, where the coefficients can be determined explicitly and also read off from the expression of the species scale in this simple case. So with that being observed, another thing that we want to compute is this slope of the species scale. And again, here, because we are choosing the canonically normalized scalars, the gradient is just a trivial derivative. So plotting this, because we have complete control of the species scale across the entire moduli space, we can compute this quantity again everywhere as a function of this lambda parameter. So then we see that in the in one end of the limits, we approach the coefficient of 1/8, which is predicted, or which is predicted to be the emergent string limit by observation. And also in the other limit, we approach this 1/11 minus 2 times 10 minus 2 limit, which is indicative of a decompactification limit, which is indicative of a one-dimensional decompactification limit. And then now we know what this decompactification limit is, and it's simply M theory. And the surprising thing from this is that by simply studying the one-loop contribution to the species scale, and in addition to the emergent string conjecture, we can predict the existence of this higher dimensional M theory that type 2A string theory decompactifies to. But with all of this exciting story, it is nevertheless still consistent with what Damien, Cameron, and Max have proposed, which is that this gradient, the slope, is bounded universally in this moduli space by this in this instance, because we're working in 10 dimensions, it's simply 1/8, which is consistent with what was predicted. So now we have done one example in 10 dimensions, and our paper has explored other 10-dimensional theories with the same amount of supersymmetry, which is 2B, and also half the amount of supersymmetry, which is heterotic. But as with the time constraint, maybe it is best to just go to the other end of the extreme, which is going down in dimensions and also reducing the amount of supersymmetry. And in this case, an example that we have looked at in our paper is 5D n equals to 1 theory, which can be constructed by compactifying M theory on a Calabi-Yau threefold. So the starting point so again, we want to see what the first curvature correction to the action is. And the starting point is by considering what the first correction to the M theory 11D supergravity is. And it takes on the following form, where T8 is some 8 tensor and epsilon 11 is again the 11 tensor with 11 indices. And this has been studied by, again, Green and collaborators. And the explicit form of these tensors can also be found in subsequent papers by Grimm and collaborators. So then if we take the structure of the first curvature correction in 11 supergravity and compactify this on a Calabi-Yau threefold, what Grimm, Savelli, and Weisenbacher have observed is that the TATAR to the fourth term reduces down to the following expression, where it becomes a R squared correction in the 5D n equals to 1 curvature expansion. So then placing this expression back into our curvature expansion of our 5D n equals to 1 theory, we can see that the first correction to our theory appears at R to the square term, and the coefficient is dependent on the geometry and topology of the Calabi-Yau, where V here denotes the volume of the calabi-yau, and the where this appears because we're also reducing the 11D Planck scale down to the 5D Planck scale, and J is the Kähler form of the calabi-yau. So with that,
David, sorry.
Yeah.
In about 5 minutes, you will enter question time, just to let you know.
Oh, thank you. So with that, we can expand this Kähler form in terms of a bases of two forms, where each of these two forms are Poincare dual to a divisor. And these xi's are what are called the Kähler parameters that parameterize our Kähler cone. So with this expression, we can write down what the prepotential of the calabi-yau threefold is in terms of these Kähler parameters and the triple intersection number of our calabi-yau. And with this prepotential, we can also write down what the metric is on the moduli space by looking at its double derivatives in terms of the Kähler parameters. So with that knowledge, let's apply that to a specific calabi-yau. And this choice of calabi-yau was studied in Green, Morris, and Schrominger 95, and also Green, Morris, and Baffa in 96. And this is the calabi-yau's assisted representation, from which we can read off the Walls data of this calabi-yau, and it is as following, where the C2x1 denote the second integrated term class associated to the first Kähler parameter, and this is the second one. So then we can also read off what the prepotential is, knowing the triple intersection number of this calabi-yau. And on the right is the shaded region is the Kähler cone. But because we are expressing things in terms of the volume of the calabi-yau, we can make a choice of normalizing this overall volume to 1. And what that amounts to is restricting to a codimension 1 slice in this Kähler cone. And that will be the moduli space that we will be focusing on. So a solution to the solution to setting the overall volume to 1 can be found by setting the Kähler parameter by reparameterizing the Kähler parameters into a canonically normalized scalar, such that the moduli space along the slice in terms of the delta parameter is flat. So plugging that ansatz back into our expression of what the species scale is, which appears as the coefficient in front of the R squared term in the 5D n equals to 1 action, we can see that, again, it's just a function of these normalized, canonically normalized scalars. In this case, it's -1/2 because it appears in front of R squared. So then we again plot this behavior as a function of this scalar across the entire moduli space. Of course, this is again restricted to the volume 1 slice. And we again observe that because we can compute it everywhere, we can also show that where this species scale is maximized and compute its value in closed form. And again, if we specify a lower effective energy of energy cutoff, we can compute the diameter as a series expansion in terms of these this small mu parameter. And again, away from the center of the moduli, we see this exponential fall off of the lambda species scale that is consistent with the observations made before. So with that, we can also again return back to computing the slope of the species scale. And in this case, what we observe is that because there's only one infinite distance limit in this setup, it only as we approach this asymptotic limit, our slope asymptotes towards 1/3, which is an emergent string limit. And in terms of the geometry, what we observe is that there is a shrinking K3 surface in this asymptotic limit, and we know that can be constructed by, and we know that is a heterotic string by simply wrapping M5 branes on that shrinking K3 surface. And again, by simply studying what happens to the slope in the infinite distance limits, and just looking at the coefficients of higher curvature corrections, we can see that we can predict what occurs in these infinite distance limits. So nevertheless, again, with all this exciting physics, we still observe that the slope is bounded above by this constant, which again, because we're working in 5 dimensions, it's 1/3. So due to the time constraint, I was only able to go through 2 examples, but in our paper, we have done all of the examples listed here, in addition to the 40 n equals to 2 case, which is constructed through type 2 theories, compacted ion collapse done in a separate work. But in each of these cases, we were able to compute the species scale as the coefficient of the higher curvature corrections. And we were able to demonstrate the computability, we were also able to compute explicitly where the desert, where the species scale is maximized. And in addition to that, as a function of mu, we were able to compute what the coefficient, if we were to put the diameter in this form, what the coefficient of alpha and b would be. And at last, in all of these cases that we have observed, that we have examined, we consistently observed that the slope of the species scale is indeed bounded above by this order 1 constant that only depends on dimension, with the exception that 8 dimensions and 4 dimensions have some subtle adjustments that have to be made. And with that, I'd like to thank you for your attention.
Okay, thank you very much for the very nice talk, David. So now it's time for questions. Any questions from the audience? Okay, go ahead, Nacho.
Hi, David. Thanks for the talk. One question. Do you always expect to have like just one maximum of the species scale, like a single desert point, or you would expect that maybe in some, I don't know, more complicated setups, you could have several of them?
I don't think there's any first principle reason that we would only expect one desert point. So certainly in more exotic cases, I can see that there are points at which the desert does indeed you have multiple points at which the species scale is equally maximized at those points. And it's in the particular case of, say, type 2b, although we do observe 2 maximal points, this is the exception to one exception to what you said. So in type 2b is we do indeed observe 2 equally maximized species scale occur at 2 points in the moduli space, but it turns out that these 2 points are simply just related by an SL2C transformation, so we identify those 2 points together. But in the particular examples that we study, there are consistently only one desert point here.
Okay, cool. Thanks.
Yeah.
Okay, so we have a couple of questions. Yeah, go ahead, from Chicago.
David, thank you for the very nice talk. Can you tell us what scattering constraints bring to the table? They should put some bounds, certainly on that 10D story, no?
Certainly. So a little bit of maybe history is that these terms that were computed in the R⁴ coefficients were done by examining these 4 graviton scattering amplitudes, and so if we understand precisely what if we trust what we think would happen for the species scale in these infinite distance limit, we should indeed be able to say something more concrete about higher point graviton scattering amplitudes. Is that the question?
I think we're thinking of just people using effective field theory S matrix bootstrap type arguments, or putting bounds on the allowed values of the R⁴ and there was some range where, say, type 2b fell into that range, and type 2a as well, with some maximum value, I thought. But that was a purely EFT argument, I think, from tree level scattering.
I see. So then the range at which that scattering amplitude is allowed to appear should be consistent with the range at which we see the lambda species scale to exhibit.
Yeah. Something
I think you can have an upper bound, but I don't think you can, for example, put bound on grad lambda over lambda, because that's very dependent on the moduli dependence. Yeah, so grad lambda over lambda is really a statement about coupling of phi to the R⁴.
Yeah.
And I don't think there are bounds in that, but there might.
Yeah, maybe you extend the graviton scattering to include the
With like scalar external legs.
Yeah.
Thank you for the question.
Thank you.
Okay, so maybe one last question from Dieter.
Yes, hello, hi, thanks for the very nice talk. I have a question about the identification of the minimal black hole radius with the species scale as you have introduced it, that you mentioned in the beginning of your talk. Actually, I think there could be subtle differences, namely in terms of log corrections. That at least what we found out in our work, that indeed the species scale, as you introduced it as a coefficient of the higher order curvature, indeed provides the UV cutoff, for example, for the string tower, the string scale. But on the other hand, we also saw that the minimal black hole radius could receive some additional, even not so small log corrections. I mean, I think these were also seen before in some other papers of the Spanish group. So, for example, the minimal black hole radius for the string tower is something like the string scale ms times log ms. So, can you comment on those log corrections also from the point of view of the higher order curvature corrections?
So in the case that we were looking at, we weren't seeing these log corrections in our definitions. We actually do precisely, say for example, in this 2A example, we do indeed precisely produce that M string limit.
So you produce M string, but as I say, in a different approach, I think you would get the log corrections in addition. I mean, they are multiplicative, so they're even not so small, because if the string scale is small compared to the Planck scale, then you get a sizable correction. But I was wondering if there's a way to see these log corrections also from the EFT point of view, in the way you derive the species scale.
Yeah, I'm sorry, I haven't thought too much about the logarithmic corrections, but thank you for pointing it out. I'll definitely give it a look.
Thank you.
Okay, so I don't see any further questions. So maybe let's thank David again for a very nice talk.